All right, we're back. Here's part 2 of the lecture. It's not too much longer. I'm just going to go through a couple more examples of different types of titrations and then briefly talk about how indicators are important and the choice of your indicator is important in a titration. So this information here is just a quick reminder of how you solve for weak acid titrations whenever you are adding a strong base. Very quickly, if you have something before the equivalence point, so you would have to obviously do some stoichiometry to determine what the equivalence point is. But if you are adding a strong acid and you stop the addition of the strong acid before the equivalence point, then you've consumed a portion of the acetic acid, which is your weak acid, and you've created a salt in water. Well, that salt contains your acetate ion, which is your conjugate base, and then you are able to implement the Henderson-Hasselbalch equation because that's all that's present in solution at that point, and water. At the equivalence point, you have a limiting reagent, you have both your acid and your base that both run out at the same time, so technically they're both the limiting reagents, and the only thing left in solution is your salt and water. Well, since the salt contains the acetate ion once again, that is undergoing salt hydrolysis, and in this case you will have to find the Kb because it's acting as a base. You determine the concentration of your ions in solution and then determine the pH from that. After the equivalence point, there's no big deal on this one. It's just you have an excess amount of strong base. That strong base is the primary controller of the pH at that point because there's no more weak acid. So you just do a normal pH problem where you take the concentration of the OH minus, you do 14 minus the POH to get your pH. All right. So if you were given a sample titration curve and you had to determine if it was a strong base, a weak base, a strong acid, or weak acid titration, there are some iconic things you should look for on your curve. Immediately you should start to notice the first point is that the starting points of both of these acids are different. Weak acids have a higher starting point for pH. Stronger acids have a lower starting point of pH because of the differences in their acidity levels. And then also you've got a difference in the starting point. There's a loop here, also called a curl. So there's a little bit of a tail end on the weak acids that's iconic to our weak acid titration curve. The linearity of the strong acid means that it has a steady increase in pH, but it's still not going to cause a drastic pH because of the excess amounts of strong acid. Once we get past the linear kind of flat portions of the titration curve, you need to look at the differences between the vertical sections. So weak acids have a short vertical section, whereas strong acids have a long vertical section. How do you find the equivalence point? You take the equivalence point is in the midway between the tallest and the shortest part of the vertical section. So for this red line, the strong acid, your equivalence point is going to be about here, which if you look over here is about a pH of 7. And that makes sense because this actually is a titration between a strong acid and a strong base. The main difference between that and weak acid is that the weak acid has a much shorter vertical section, and so the midpoint is much higher, and you'll notice that that's around pH of 9, which is a basic equivalence point. So those are some of the things that you should notice immediately whenever you're looking at titration curves. Also, in the end, the two curves overlap one another here because the only thing at that point that's present in the solution is your strong base at this point. So there's nothing else controlling the pH but the strong base. So if you're using the same amounts or the same molarity, you're going to end up with the same shape curve at the same points. Last thing on this one is that since we have a weak acid and partial neutralization is occurring before the equivalence point, then at this point we have created a buffer because you have a weak acid and its conjugate base present in solution. So the buffer region is this long flat section here. And there's an important point in here that's called the half equivalence point that I'll talk about at the end of this video. So everything I just said is right here. So I'm going to scroll down and let you guys see that in written form if you need to. Take a minute and look at that. All right, I have a problem for you for a titration. This is going to be actually a very easy problem you don't have to do before, during, and after, because if it's actually asking for the equivalence point, then you're looking for the point at which the moles of the acid is equal to the moles of the base. So this is just a basic stoichiometry problem. Since you have your BCE, essentially, you have your cyanic acid and your sodium hydroxide. You need to write out your BCE, so you're making salt and water, so there's HOH and there's sodium cyanide. In this example, it's a 1-to-1 ratio. That's pretty much the important part of this BCE. So remember that you're always starting with the thing you know everything about. Since we know everything about the acid, this would be considered our titrant or our standard. Two words for the same thing. Since we don't know everything about the sodium hydroxide, that would be our analyte. So what are we looking for? We are looking for the milliliters or the volume of the base added. Because I want to know how many milliliters of this base do I need to add to the acid in order to get to the equivalence point. So this is actually quite easy. You start with your M times V to get your moles of the acid, and then you'll do your mole-mole ratio to get your moles of your base, and then you'll determine the volume with the molarity. So here's our molar concentration, 0.48 molar moles per liter of the HCN. Sorry, bad habit of acids that way. And then you have your milliliters used, which I'm going to convert to liters, so 0.050 liters of HCN. And then your mole-mole ratio. So here so far we've canceled out our liters. You got 1 mole of HCN and 1 mole of sodium hydroxide. Last part here is to notice that we have moles on top still. I need to solve for volume, so I need to flip my molarity as my last step. So I've got the molarity of 0.75 moles per liter. So here, when you solve, you get 0.032 liters, which is the same thing as 32.0 milliliters. So the equivalence point for this is if you've added 32.0 milliliters, you would that would be the point at which the moles are equal, and then your equivalence point, you should be able to tell the pH from that because you know it's a strong base and a weak acid, so it should be in the basic region. You can do the math for that based on what you previously just learned. Okay, so quick review. This is going to be use of indicators, and you're very familiar with indicators because you did the lab where you looked at the different pHs and the different colors that each indicator underwent whenever it went through all the pH changes of your buffer solutions. So optimally, if you were trying to do a titration, you would want your equivalence point to be where your endpoint was occurring. So the indicator changes colors at the endpoint. Changes colors. So if your equivalence point and your endpoint are very, very close, then you'll get a very accurate amount of sodium hydroxide or whatever titrant you're using to determine the equivalence point of that particular reaction. But most of the time we don't have that occurring. So you're going to try to choose the best indicator for your given reaction by looking at a list of indicators and where they change in their pHs, or where they change their colors, what pHs they would change. And another thing to notice is that whenever we have our vertical section, we really want a pH, we really want an indicator to change anywhere within the vertical section. So if you can choose your indicators appropriately, you do have a wide range that you can use here. It just depends on what type of reaction you're doing. And the main reason we can't always choose exactly what we want is because of this whole single drop of the titrant that can cause a big, humongous pH jump, so sometimes it's hard to choose. Alright, so we already talked about that, we already talked about that. Basically, in this example, if I wanted you to choose an appropriate indicator, you would choose one that would change closest to the equivalence point. Well, the equivalence point is right in the middle of the vertical section, and so the thionyl blue would be a better choice than methyl red, because methyl red is going to change more at about a 5.5 pH, whereas the thionyl blue changes about a 9 or an 8.5 pH. So you look for something that changes where your equivalence point should be. In this last one, in this example, I just give you a little bit of more information about how indicators work. They're organic molecules that have the ability to protonate and deprotonate. So we actually treat them as weak acids. So I like to label it HIN. That's not indium. It's just a short name for a really humongous molecule. So in the protonated version, in the acidic version, this example shows you that is blue. If you add enough sodium hydroxide or something that's going to react with it, then the H and the OH get together to form water, and it's going to deprotonate to the basic form where it's lost the proton. So that's why we use these in titrations, because obviously in titrations we're transferring it between two different forms, the acidic form and the basic form, based on if we're adding a strong base or a strong acid or a weak base. Just depends on what you're adding. So that's why it's very important to choose the correct indicator so you get the correct change at the right point. in this equilibrium reaction here, you can actually determine the Ka from this, because you know that liquid water, if you found the correct concentrations anyway, you know that liquid water is irrelevant. So when you set up your Ka expression would be the product's concentration of hydronium and the anion over the protonated version, which is the HIN. So if you actually know all of these, you can determine the Ka of an indicator. Or you can just take the Ka of an indicator and figure out how much you need or how much hydronium is produced. So with this is actually an application of Le Chatelier's principle in these following two questions. What color with the addition of a base will the indicator turn? In this example, if you add a base, the hydroxide will react with the HIN form, causing a shift to the right as it gets consumed and forces the formation of the hydronium ion. So we have our red form that's going to be favored. In the next example, what color does this indicator turn with the addition of the acid? So if you add acid, you're actually going to increase the hydronium. Increasing the hydronium is going to cause a shift left, so the blue form would be favored. So all this is acid-base reactions and Le Chatelier's principle in the form of an acid-base titration in the formation of two different colored ions. And most of the time, we have to use enough indicator to show a color change, but sometimes the color changes, it's impossible to see with the naked eye. So a noticeable color change is going to occur whenever 1/10 of the indicator has changed. So in this case, if your indicator, the IN form in this case was our red form, and the HI, the protonated version, was the blue form, when one molecule for every 10 molecules present changes color overall as a net change, then we can see that color change and we would call that our endpoint. This is important on the next slide. Alright, so for example here, at what pH will the indicator bromothionyl blue change color? That means that we need to determine the H3O plus present in the solution, so we can determine the pH from that. We're given the Ka value, great. This is just a quick hint. If you take the pKa of this, which is the negative log of that concentration, you get 7. This is why bromothionyl blue is a great indicator for a strong base, strong acid titration, because it changes that pH of 7, which is good because the equivalence point of a strong acid, strong base is 7. Alright, so back to the example though. I'm going to go back to our generic form for an indicator, where you have the IN, the anion forming, and H3O plus forming. If we can determine this, then we can get the pH. Since we already have been told that if 1/10 of the indicator changes is protonated or deprotonated, then we will see a color change. Then that's going to be important. So earlier where we had IN minus forming from HIN in this example, we know that at that point, when it's the 1/10 ratio, then that's where the color change will occur. We also already talked about the Ka value for this, where we had the hydronium ion times the indicator, the deprotonated indicator, over the acidic version of it. That would equal the Ka. Well, we have the Ka, 1.0 times 10 to the negative 7th. We know that the color change will occur when the ratio of IN over HIN is 1 to 10. We know that's when the color change occurs. Since we know everything but the hydronium concentration, we can solve for hydronium and therefore solve for the amount, the pH at which it's going to change. So in this area, this is hydronium times 1 over 10 equals 1.0 times 10 to the negative 7th. If you multiply both sides by 10, you get hydronium ion concentration equals 1.0 times 10 to the negative 6. This right here, take the negative log of that to give us the pH of 6. So it's going to change at a pH of 6. It's good to use for anything that's in the range of plus or minus 1 though. So this would be great to use between pH of 5 and 7. And so the rule for that is you choose the correct indicator by taking the pH that it changes plus or minus 1, which is going to serve as your best, as long as your equivalence point is in this general region, then that'll be a good indicator for your titration. So looking at these two graphs, we can